Namaste everyone. Welcome to optics class, ray optics class. We have solved some problems regarding refraction through a single surface. Already I have told that that idea of solving the problem helps you to derive lens maker's formula. Now what do you mean by lens maker's formula? Why it is called lens maker's formula? Now suppose you have anybody is having eye defect. That means either myopia or hypermetropia. Suppose they can't see far away object, it doesn't get focused at a proper position. Then that problem arises. If you can't see a near object or a far away object, that problem arises because these ciliary muscles in the eye cannot compress the eye lens to a certain extent. In a normal human being, the ciliary muscles can expand and compress the eye lens to that extent that you can see all the objects. But as because of some problems, the ciliary muscles lose their ability to compress the lens to a very large extent or expand also. So the eye lens cannot form the image on the retina. So we have to help the eye lens by keeping another lens in front of our eye. According to whether it is myopia or hypermetropia, we use concave lens or convex lens. Now, when the person having myopia or hypermetropia approaches doctor will see what is the problem with this person, whether he or she can't see the far away objects or the closer objects, whether the image is formed in front of retina or away from the retina. If you want to bring the image back to the retina, what type of lens he has to wear, whether it is concave or convex. Accordingly, doctor will prefer a lens. Doctor will say you have to wear a lens of 0.25 power, 0.1 power, minus 0.5 power, minus 0.3 power, a diopter, 0.3 diopter, minus 0.2 diopter, like this. Or doctor will prefer a lens of so much focal length. So doctor will write, you have to wear so much of power or so much of focal length lens. Now you will take it to the shop, you will ask the lens maker to prepare such a lens because doctor has written. He will look into that. If you want a lens of 0.5 power, 0.5 diopter power, or I'll write focal length. So suppose the doctor has preferred a lens of focal length plus 2 meters, then shopkeeper will ask you what type of lens you want. Do you want a lens made up of fiber, plastic, or glass, flint glass, this glass, that glass, or do you want a lens made up of diamond? Which material? So refractive index of the lens, it is left to you. Focal length is given by the doctor, right? Refractive index is left to you. You will say, I want this and this type, I don't want diamond, I want only fiber glass, that spectacles. Okay, that is selected. Refractive index of the material of the lens is selected. Now, if the lens maker has to prepare that material lens and so of refractive index NL, how much curvature he has to give for both the sides so that its focal length, that means when the parallel rays are incident on the lens, where should they get focused? That is called focus, and this focal length should be 2 meters. I think you are aware of all these things which you have studied in your lower classes. Every lens has a focal length. Every lens is characterized by a focal length. What do you mean by focal length? When parallel rays are incident on a lens, after refraction through both the surfaces, they meet at a point. And if it is a convex lens, if it is a concave lens, they appear to meet at a point. They happen to, or they diverge in such a way that they appear to diverge from a fixed point here. This is the focus, and this is the focal length. Whatever it is. So if parallel rays are incident on a lens, after refraction, either they converge at a point, or after refraction, they appear to diverge from a point. You use the words like this, right? Just listen to the words. If parallel rays are incident on a convex lens, after refraction they meet at a point, or if parallel rays are incident on a lens, after refraction they diverge and appear to diverge from a point. Appear to diverge from a point, they converge at a point. Here not appearing to converge at a point. They really converge at a point. At a point, they appear to diverge from a point. That is not real. Appearing to diverging from this point. Okay, so that is the focal length. And if the lens maker using this material suggested by you and to produce a focal length of 2 meter according to the doctor, how much radius should be given to the two surfaces? What is the radius of each surface or both the surfaces? That is what he has to select. So he should select this R1 and R2. And if we want to select this R1 and R2, radius of this, the center will be here. Radius of this, the center will be here. What should be the radius given to both the surfaces? Then you have to connect focal length, refractive index of the lens, as well as the surrounding medium also. So I will call this as N2, refractive index of the lens. Refractive index of the surrounding medium, I will take it as N1. So this is N2, this is N1, and radius of curvature of this, radius of curvature of this R2, then 1 by F is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. This is called lens maker's formula. Now doctor will prefer this one. Which focal length lens you have to wear in order to correct your image formation process. This is selected by you. Surrounding medium, however, it is air, and these two will be given by the lens maker. Lens maker will create a curvature for both the surfaces and he will prepare the lens. So that is why it is called lens maker's formula. This is the thing what you have to get at the end of the derivation. And lens is an optical medium bounded by two surfaces, and either the two or at least one surface, one plane surface. This is plano-convex, this is plano-concave, biconvex and biconcave. Double convex, double concave or biconcave, double convex or biconvex, plano-concave, plano-convex. You can have any type of lens. Now, what is a thin lens? Now suppose you have a lens like this. This is a part of a sphere, its center is here. This is a part of a sphere, its center is here. Now compared to the radius here of this surface, this thickness is very small. Compared to the radius of this surface, this is the radius. Compared to this radius, this thickness is very small. So if the thickness of the lens is very small compared to the radius of curvatures, then it is called a thin lens. Thin lens is one whose thickness is very small compared to the radius of curvatures. Okay, that is okay, right? What about a sphere, glass sphere? In the previous class we did one problem, we solved one problem, glass sphere. If it is a glass sphere, can you call it as a thin lens? Never, because its radius is smaller, thickness is larger. How do you call it as a thin lens? Thickness itself is larger, much double the radius. It is not a thin lens. So now let me take a thin lens. Okay, you take a pen and paper, that is very important now. Take a pen and paper, start drawing the diagrams. Don't watch this video as if you are watching a movie. This is not a movie, this is a educational video. You have to draw and you have to study as you watch. Please take a paper, please take a pen, and you must do that. And if you are not doing it, switch off your commodity, whether it is a mobile or whether it is a laptop, switch it off and go away, because that is a better option. You have to do it now. I'll take a lens. Okay, it's a thin lens because its radius is much more than its thickness. Now the center of one surface will be here, center of another surface will be here, somewhere, join them. That is the principal axis, line joining the two centers of curvatures, and the radii of the two curvatures may not be the same. It may be same, then it is called biconvex, and equiconvex it is called if both the radii are same. That may not be same also. Okay, now the center of this surface is somewhere here and the center of this one is somewhere here. I'll name the surfaces A, B, C, D. O is a point object kept on the left side of the lens. Consider two rays of light coming from the point object O. One moving along the principal axis, passing undeviated, because for this surface it is passing through the center. For this surface it is passing through the center. It is incident normally on both the surfaces because this is a part of a sphere. So the center is here. This ray is going to pass through the center. Normal incidence passes undeviated. That is okay. Good. What about the other ray? Consider another ray. Now we should be very careful. Let it be incident on the first surface. Okay. Now this diagram I am going to draw it and I will draw so many things here. Then we will refine it afterwards. I will draw it again later. But you can also do the same thing. Now, sir, what happens to this ray? That is very important now. Okay. A ray of light is incident along like this. Now, suppose N1 is the refractive index of this medium outside and N2 is the refractive index of the medium of the lens. Let us assume that this is rarer, this is denser. Say this is glass, this is air. When a ray of light is traveling from rarer to denser medium, it bends towards the normal. You know it. But where is the normal? This is the original direction, correct? This is the original direction of the ray of light. And it should bend towards the normal. If you want the normal, you have to complete this surface. This is a part of a sphere. Of course, you can scribble it like this. This is the part of a sphere. Its center may be somewhere here. Now join this. Forget about this surface. That is later, right? Forget about the second surface. What the first surface will do, join this point and this. This is the normal, correct? This is the normal. And the ray must bend towards the normal instead of going like this, because rarer to denser movement. So I will draw this here. It bends towards the normal. Am I right? It has bent towards the normal. Now you will get the previous idea, that the problem, idea of the problem. What is the idea of the problem? Suppose this surface was absent. What would have happened to this ray? Suppose we were having only this surface. What would have happened to that ray? That ray would have traveled and bent towards the normal and would have traveled straight. Am I right? So, if this surface was absent, ADC, what do you mean by surface ADC is absent? This is glass, continuous glass. There is no surface here. It is continuously the same medium. That means, if this is absent, this ray may not have turned back again. It should have traveled like this. Now this can be shown here like this by dotted lines. So I will show it using the same line has to be continued like this. So this is where only first surface will form the image. I call it as I1. Got it now? In the absence of the second surface, first surface alone, this one, will bend the ray of light towards the normal, because its center will be somewhere here. C1 I will call. And this is the normal. So ray was traveling like this. It has bent towards the normal. It would have moved straight. Now, cut this surface. Cut this one. Remove the remaining glass and throw it away. Let it be air. Now we won't get this image, because the ray had got an opportunity to move back to air. So as this ray travels into air like this, now where should it bend? Now it is moving from denser to rarer. You should be very careful. I will go back again. When the ray was traveling from here to here and inside, rarer to denser, moving like this, bending towards the normal. So bend towards the normal. And it has bent like this. It has met the principal axis at I1. Remember, it is not outside air. It is not at the outside medium air. It is inside glass itself, this condition. So it has not been cut. Like this. Now can you write angle of incidence and angle of refraction here? Definitely. See again all the definitions. Angle between incident ray and normal. Angle of incidence. Angle between refracted ray and normal. Angle of refraction. First one. Now ask the second surface. The ray was moving like this. Suddenly cut the second surface. Remove it. And the rest of the things are air now. Except this one glass. This is air, say. The ray gets a chance of coming back to the same medium. Now, how do you proceed this ray? It was moving like this, bent towards the normal. Now you have to proceed this one. It is moving from denser to rarer medium. It should bend away from the normal. Which normal? Normal drawn to this surface, not this one. Correct? Because, normal drawn to this surface, not this one. Because refraction is occurring here in this surface. So if the refraction is occurring here, find out where is the center of this surface. Where may be the center of this? Say somewhere here. C2, center of the second surface, where the refraction is occurring here. I want to know what happens to this ray of light. If it was traveling straight, it would have traveled like this. Draw a normal at this point of incidence. How do you draw a normal? You have to join the center and this one, correct? If it is very disturbing, I will rub all these things, right? I will rub this one. Okay, the ray was traveling like this. Now I want to have a normal here like this, correct? I will continue the normal. The ray, instead of traveling like this, the normal is here, because for this surface, center is here. This is the normal line. This ray, which was traveling like this, should bend towards away from the normal, denser to rarer. Away from the normal means like this. It should, otherwise, if it was bending like this, it would have been towards the normal. It should be away from the normal, like this. This is the final image. Got it now? So once you form this one, for this surface, center may be somewhere here, rub this. It is incident here, join this one. This ray was traveling like this. This is the normal. If it had traveled here, if this ray was traveling like this, it is towards the normal. This is away from the normal. From its original direction, away from the normal. So shall I draw it again? I'll draw it again. Of course, derivation is only mathematical. You know the theory behind this because we have solved the problem. We have enough knowledge within us, so derivation becomes easy. So take a lens ABC. You can also draw it again. And this is D. O is a point object. One ray of light incident along the principal axis passes undeviated, no problem. It's incident normally. Normal incidence, no deviation. Another ray of light incident like this. First bending towards this one, second bending towards this one. So finally it meets the principal axis at I. That is the final image. Suppose the second surface was absent, this would have moved straight. So you have to produce the same direction like this, right? Don't bend it. It would have moved straight to meet the principal axis at somewhere here. This is I1. Image formed by the first surface, okay, and right. And shall I name all the distances? So this is object distance from the lens, this is final image distance from the lens, and this is the image formed by the first surface, and N1 is the refractive index of the medium outside, N2 is the refractive index of the medium inside. Now I have to get the answer for this. Okay, we will do it one by one. And you know, the final formula should be 1 by F is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. This should be the final formula. At the same time, you must remember that you have to use this formula twice. N1 by minus U plus N2 by V is equal to N2 minus N1 by R. This is what you have to do. Okay? Right. Shall we apply it to the first surface? Now, ask the first surface, our same interview with first surface. Surface ABC. Do you have any object in front of you? Yes, sir. I have an object. I receive many rays of light. And out of them, 2 rays of light are here. And if I produce them backwards, I get object here. So you have an object. What did you do with this object? Sir, I bent the 2 rays like this and I formed the image at I1. So shall I show it here? So I will rub this formula because you know this. I have the first surface and the second surface is not yet produced and it has not yet been carved in. And so it is like this. And here is the object and a ray of light coming like this. Of course, this passes undeviated, and if you complete this, this here will be the center C1. And shall I call this as radius R1? I can call the radius R1. Now this is the normal. The ray which was traveling like this bends towards the normal and meets the principal axis at this point, right? This is the I1 and this is V1. Am I right? This is V1. This is N2. This is N1. So shall I write this is B, this is A, this is C. Second surface we are not at all bothered. This is I1, this is R1. How, sir? Incident ray and normal. Refracted ray and normal. Are they? They are correct, right? Now, let us write the formula. Refractive index of the medium n1 by minus u plus n2 by v, n2 minus n1 by r. Refractive index of the medium where incident rays are present, n1, no problem. By object distance, OB, of course, minus object distance, it is in the left hand side. So I will use this sign conventions again and again, and you know that once you derive the equation using sign conventions, then the formula is ready, and it is ready for any type of surface, whether it is convex lens or concave lens. For any lens you should be ready. So let us use the sign conventions again and again here. So OB minus OB. Why, sir? Because it is on the left hand side. What else then? 1 plus n2 by v, refractive index of the medium where refracted rays are present, that is n2 itself, by image distance, that is on the right hand side. So this is the coordinate system for us. It is on the right hand side and it is v1, and shall I write it as bi1? It is positive. bi1 is equal to refracting medium refractive index, incident medium refractive index, by radius of curvature bc1. So it is plus bc1. Why? Because it is on the right hand side. It is plus bc1, right? One equation. So shall I write it in a proper way? n1 by minus or minus OB, n1 by OB plus n2 by bi1 is equal to n2 minus n1 by bc1. Okay, that is one part. Now again we have to go to the second part. What is the second part? Ask the second surface. Surface 2, surface ADC, surface ADC, this one. Are you receiving any rays of light? Yes, sir. How many rays of light you receive? Many rays. Name any two. One is this one, sir. Another is this one. I receive 2 rays of light. One is moving like this, another is moving like this. Now, what did you do with these 2 rays? Sir, I produced them and I bent them after going to air. And when they went to air, I bent them and I made them to form the image at this point and at a distance of v. Okay. Do you have any object and do you feel that these rays are coming from any object? Surface ADC says, they must be coming from an object, sir. Wait a minute, I will see. I will produce them backwards. I will produce them backwards. They never meet, sir. So I will do one thing. I will produce them forward. I will produce them forward. So I1 acts like an object for the first surface. For second surface. This image formed by the first surface acts like an object for the second surface, because second surface, very poor guy, if it was putting the rays back, they never met, no object. At least we will take this as an object. If you produce it forward, you get an object here. So I will list the values now. For the second surface, if you ask, where are the incident rays? n2. Incident rays are here, n2. And where are the refracted rays? n1. Where is n1? Okay, here, back to this, n1. Coming back to air, n1. And what is the object distance? For this surface, this is the object distance. Where is the image distance? This one. So shall I write this one? Okay. So same formula, n1 by minus u plus n2 by v is equal to n2 minus n1 by r for the second surface. Okay. If you want, I will draw one more diagram for the second surface. We will do that properly. Okay. Only second surface. Which one? This one. ADC. This is glass now. I am not bothered about the first surface. I am bothered about only the second surface, ADC. And this is the principal axis. And you know that center is somewhere here for this surface, right? Center will be somewhere here. And one ray, this is like this. And I will call that ray n1, n2. I will call it as n1, n2. So n1 is here, n2 is here. It was moving like this. And another ray was moving along the principal axis like this. It moves straight, and these 2 rays are, and how it is bent like this, because if you draw a normal here, if you draw a normal, this will be the normal, and it is like this. This ray, instead of moving like this, it has bent away from the normal. That means like this. It has bent away from the normal. So these are the 2 rays, and this is I1. Of course, it comes away a little bit away. If you want the same type of diagram, It should be like this. I have to search for different chalks. Yes, like this, and it is like this somewhere here, right? So this is I1, which is V1 from here. From this surface, it is V1. Okay, like this, and this is final V. Hope you can understand this diagram, right? So one ray here inside the medium, like this, bent, formed at I in final image. But if it is produced backwards, they meet. Otherwise, they don't meet at all. So for the second surface, we will write. So this is N2, this is N1. Okay. Refractive index of the medium where incident rays are present. Second surface, where are the incident rays? Inside myself, glass, N2. By object distance, negative of object distance. Where is the object? Object is here, because these two rays never meet at the backward direction, whereas first medium had no problem, such problem. They were meeting here, so this was the object distance. Now they don't meet at all, they meet here, so this one, di1, and it is positive. Why? Because it is on the right hand side. For this surface, it is on the right hand side. This negative is in the formula itself. Plus refractive index of the medium where refracted rays are present. After refraction, they come back to the same medium here. So that is N1 by image distance. Image distance is, final image is formed here. So they meet here actually. So it is a di, right? I think I can see it here, di. It is positive, right hand side, is equal to N2, refractive index of the refracting medium N1 minus incident medium. Of course, this formula is as it is a formula. Here everything gets interchanged. Refractive index of the refracting medium minus refractive index of the incident medium. Refractive index of refracting medium is N1 and this is N2. This N1, N2 is different. Okay, N1 minus N2 by radius. Radius of this surface is on the other side. It is the second center. So the curvature of this and curvature of this may not be the same. This we will take it as R2, but it is on the left hand side. So shall I write it as minus R2? Now, another thing is the problem that you have done in the previous class and this derivation has a small difference. What is that? While taking this one as the object for the second surface, what did we do there is, it was a sphere and there was an object and there was a second refraction and like this. For the first surface, this distance is V1. But when you take it as an object, this distance, only from the first surface the ray will meet here. But for the second surface, if this has to act like an object, we took this as the distance because from here. But in a lens, there is no problem as such. There is no such problem because lens is very thin. Whether you take the distance of this image as an object for the second lens as bi1 or di1, it is one and the same. Because thickness of the lens is not like a sphere. Sphere has more thickness, but lens is a very thin lens. So shall I write bi1 and di1 almost the same? So shall I replace this one? So bi1, since the lens is thin, is almost equal to di1. So what this formula will turn into? N2 by minus bi1 plus N1 by di is equal to, so shall I bring this minus to the numerator so that I can multiply it here? Minus of N1 plus N2. So what this will become? N2 minus N1 by plus R2. Did you get that? This minus is brought here. Minus N1 plus N2. N2 minus N1 by R2. This is equation 2. Okay, this is equation 2 and this is equation 1. Okay, and I will write this one as not R2, I will write it as, what is that R2? It is DC2, right? DC2. This is minus DC2 and this is plus DC2, right? I'll write it as DC1 and DC2, right? Because I will write it in the distances. Now, can you add these two equations? I think we can add them. When you add it, what you will get? Yeah, because left hand sides here you have N2 minus N1 common. Okay, what you will add here? N1 by OB, I'll write it here first, N1 by OB and plus N2 by B1, N2 by B1, BI1, okay. Left hand side of this is over. Left hand side of this one. minus n2 by bi1 plus n1 by di. Okay? Minus n2 by bi1 plus n1 by di is equal to, so when I add these two, shall I take n2 minus n1 common? Okay? What I will get then? n2 minus n1 common outside. Put a bracket here, don't leave this, into, what is here? 1 by bc1 plus 1 by dc2. Of course, I have interchanged this and I made it positive. 1 by dc2 radius, or n2 minus n1 by bc1, n2 minus n1 by dc2. Anyway, now this gets cancelled. That's the only difference you have here. We need not subtract the distances from the thickness because thin lens it is. So bi1 and di1 can be taken almost same. So that gets cancelled. What is remaining? n1 by ob plus n1 by di, right? n1 by ob plus n1 by di. Okay, where is it? Yes, that is equal to n2 minus n1 into 1 by bc1 plus 1 by bc2. Now write uvr, whatever the thing you want. Apply the sign conventions again. n1 divided by, what is ob? Ob is the object distance. And okay, yes, n1 by u, right? Or it is minus u on the other side. Can you see this diagram? Or shall I write this one here? That becomes easier. So I will shift that equation here so that I can apply to the diagram very easily. So I will copy that formula. n1 by ob plus n1 by di is equal to n2 minus n1 into 1 by bc1 plus 1 by bc2. You have this in form equation in your book, so no problem. Is it all right? Right? n1 by ob, n1 by di, n2 minus n1 into 1 by bc1 plus 1 by bc2. So if you want to apply for this equation, the conditions here, you have to apply the sign conventions once again, because this equation is obtained by adding the equations for both the surfaces. We have written equation for this refraction at the first surface and the refraction at the second surface. Finally we got this equation by adding this. Now if you want to use this for any type of surface, because if your formula is obtained finally, then it should be suitable for all the conditions. All the conditions in the sense, this surface may not be convex, it may be a concave surface also. So if the final equation is suitable for concave also, again you have to apply the sign convention for that equation which is obtained by adding the two surfaces equations. So we will apply the sign convention once again. But while applying the sign convention here, you have the object distance on the left side, image distance, final image distance I am talking about, right hand side, and this is the coordinate axis here. And what are these radii, R1 and R2? So if I write it like this, suppose this surface is here, first one, then its radius will be here, right? It will be on this side. This is R1. What about, this is the first surface, ABC. And what about the second surface? Second surface will be here and its completion will be here and its radius will be here, R2. So hope you have followed. And here, this is the coordinate system, okay? This surface is here and this sphere is completed here and this is R1. This surface which I have marked in another color, pink color, radius comes here to the left hand side. So we will substitute n1 refractive index. Refractive indices as such, they don't have any sign conventions because they don't come under any distance. So refractive index of the medium, okay, divided by OB. OB is the object distance. That lies left side, right? So minus u. Okay, because again I will apply the sign convention, plus, because this is a combined formula. I want a final formula which is suitable for any type of occasion. n1 again by image distance di, this is in the right side, right? So this is the coordinate system, this is the right side. So that is image distance by v is equal to n2 minus n1, no sign conventions here, into 1 by bc1. BC1 is coming on the right hand side, right? Because this is ABC and the center of the first one lies here, and this is ADC, second surface center lies here. This is DC2. So 1 by, it is plus R1. Hope you have followed. Why plus R1? Because it is on the other side and the surface is here and the radius is this one, R1. And what about BC2? Plus 1 by BC2, sorry, it is, okay, DC2 it is actually, right? It is DC2. DC2 comes from this side to this side. It is on the left hand side, it is R2 with a negative sign. So I'll put a negative here, no problem. So 1 by R1 minus 1 by R2. Hope you have followed. R1 is this side, right hand side, R2 is this side, left hand side. So this is finished. Now bring this common n to this side. What you will get? Minus 1 by u plus 1 by v is equal to n2 minus n1 by 1, n1. This n1 common taken here will bring will come to the denominator. 1 by R1 minus 1 by R2. Okay. Now doctor has given focal length, and you have preferred the refractive indices, and lens maker will prefer the radius. Now where is the focal length? Where is the prescription of the doctor? We will do it like this. You know what is the focal length in your lower classes you have studied? If you take a convex lens, if you incident parallel rays of light, they will directly go to the other surface and meet at a point. It is a converging lens. Focal length is the distance between the focus and the lens. Am I right? So if parallel rays are incident on a lens, after refraction they meet at focus. If this is the focal length, now while finding the focal length, you incident parallel rays of light. Where is the object now? You ask this lens, you have converged all the rays here and you have formed the focus. Where is the object? Lens will look to this side. These rays are coming from a very large distance, so object distance is infinity. Now ask the lens. You have taken the rays of light coming from infinity and you have made them to come to focus. Where is the image? Image distance is at focus, right? So if the object is at infinity, image is highly formed at focus. We do this experiment when you are kids, right? Usually kids do this experiment. They take a lens and hold it against the sunlight, and all the rays, parallel rays coming from the sunlight fall on a paper and forms a point object. What is that bright point formed on the paper? It is nothing but the image of the sun. Imagine the size of the sun. Imagine the size of the image. Image is highly diminished. So image is at focus, object at infinity. You apply this condition, you will get focal length. Apply it here. Hope you can see this one. 1 by object distance, 1 by infinity, of course, minus, plus 1 by v, 1 by focal length. That is this one, the focal length is the focus is the point where the image is formed. What you will get? I will divide this. n2 by n1, n2 by n1, n1 by n1 minus 1 into 1 by r1 minus 1 by r2. This is the formula, right? But 1 by infinity is 0. So what you will have finally, shall I write it here? I think I can write it here. 1 by f is equal to n2 by n1 minus 1 into 1 by r1 minus 1 by r2. This is called Lens-Baker's formula. The name is given because doctor will prefer, if there is any eye defect, they will prefer this focal length or power usually. We will see what is the power of a lens. And you will select which type of lens you want, whether it is made up of fiber or plastic or diamond or glass. This you will select. Outside medium is usually air, right? And the medium of this lens you will select. And the lens maker will prefer the radii for the two surfaces, and he will prepare a lens of this much focal length. That is why this is called lens maker's formula, a formula which connects focal length, radii curvature of the two surfaces, and refractive index of the two media. Of course, I can write it like this way also. n2 by n1 can be written as n21, correct? n21 minus 1 into 1 by r1 minus 1 by r2. That is also possible. Refractive index of the second medium with respect to first medium into 1 by r1 minus 1 by r2. If you get a simple question for 2 marks, what are the factors on which focal length of a lens depends? Focal length of a lens depends on the material with which it is made up of, n2. The surrounding material, surrounding medium, radii of curvature of the two surfaces of the lens. So these are the factors which will decide. So focal length of a lens depends on the refractive index of the medium of the lens, refractive index of the surrounding medium, radii of curvature of the two surfaces. Very important formula. So we are going to play with this formula in so many problems, but instead of knowing the formula by only by terms, better you know by theory. Why this formula has been obtained like this, what is the theory behind this formula, and what are the significance of all these values. That is very important, and we will have few more discussion on the formula itself in the next class. For the time being, you study the derivation properly. Very important derivation, as a 5-mark derivation also. So you have to study this, and if at all you have problem, you give a message, we will clear it. But for the time being, I will stop it with this formula. In the next class, we will go along with this formula, discussion on this and a few problems. Hope you will do well and you will study the derivation properly. Ready with the formula in the next class. Hope you will do well. Take care. Thank you.